So what I'm saying is that I'm going to say that I have my base factors running from 1 to 14. Can I get a linear interactions of them? So the linear interactions means that if I had factor 1, 2, and 3, I will try to multiply factor 1 by 2, 1 by 3, 1 by 1, 2 by 2, 2 by 3, 2 by 3, 4, something like that. And I will try to form all the possible combinations such that they have all have a degree 2. So degree 1, degree 1, degree 1, degree 1. So in sense, they are of order 2. And then see if those features add any value. I think that's one of the step which I wanted to highlight in feature engineering. You come up with these ideas when you're trying to look. So that's just one way, higher order polynomial. If you think you could obviously add features which are log features, I can vouch that I have tried, and some features are really good to look on log scale. So let's say if you have a market cap of a company normalized by something, you might actually want to look at in log scale. That makes sense. Let's say if you have something uh, if there are some features which actually look at historical difference of few things, you might wanted to create a dummy feature out of it. So if event A has occurred, let's say it's going to be +1. If event B has occurred, it's going to be -1. So these kind of things you would have to do in your step. So here we have chosen one path is just to look at higher order power rather than some other hypothesis. The way to do is use a scikit-learn pre-processing tool called Polynomial Features. So I've imported it at the top. It's you go to scikit-learn pre-processing. There will be a module called Polynomial Features. What it does that you provide your data frame, you provide your matrix, and then you say, okay, create interactions out of these matrix, create polynomial features. You provide a degree of polynomial, which in this case, I think I have provided 2 or 3. I have to look at way. Yes. So what I've said is that up till this point, okay, so I've created this class, this polynomial features, and I've called its function, which is fit and transform. So what it will do is it will take the train, it will take the X feature that I have feature space, which has feature 1, 2, 3, 4 till 14, and then it will return me a data frame, which I have called here XP, effectively my X with polynomial transformations. And then this XP will eventually be something like this. It will have all the features. Okay, I'm not run it. Yeah, it will be something like this. So if you go and start to look at it, it has features like, okay, feature 12 squared time feature 13 feature. Let's just plot them. See, so there are hundreds of features now. Feature 8 time feature 9, feature 8 time feature 10. We don't know which one of them is going to be helpful or not, but it's just a way to not manually multiply them, but just get directly from the feature space. Okay, we have got it. We have used our data frame to name them. To get the name, there's a different function.
Um,
Sure.
Shiva, can I just ask you? You said it's like feature 1 times feature 12 or whatever. Isn't
Yes.
it? Wouldn't it be feature 1 plus feature 12 or feature 2 plus feature 6 squared also? Or are they actually multiplied? I wasn't so sure because it's a polynomial, right? So you
Yeah.
say a plus b squared plus
Yes. Yes.
c.
Correct. No. No. So
Yeah, it's like that, right? Like I wasn't sure. Okay,
no.
cool.
No. Sure. Sure. Tom. So
Mm-hmm.
when we are using this polynomial features, it is called polynomial features because we are creating those features. Your point is correct. So when I'm going to create a model, my feature 1 times feature 2 squared, it's one feature now. So it will get plus with another feature when I'm building my OLS model. But in feature space, this function effectively multiplies them because it's not creating an OLS model out of them. It's just giving you the feature space once they have multiplied with each other. So that point is valid, that polynomial feature does not add them, it just multiplies them. So it's creating interactions out of them. And then once we have created interactions, that's the next step, which is we use this feature as it is. So just showing an example that out of my 14 features, it has created 680 features now, which is a huge number. Like If you say that one can manually like start typing all the feature, it's hell of a job. But and then again, you don't know which feature will come out significant or not. You can only try like 10, 15 iterations manually. So once you do that, then effectively the next step you're going to fit an OLS, it exactly the same, which is, let's say, this feature. Now what we have is till 14 we already knew, but now this feature square is plus it will be like feature 14 times beta 14 plus feature 15 times factor 1 square plus feature beta 16 would be factor 1 times factor 2, something like that. In that order it will be there. If you do that, you will notice that your adjusted R square has gone to 0.226 if you do that. And one thing could happen that, okay, oh, I've created this great model which has increased my R square from 1.6% to, let's say, what, like 26% explanatory power. And then you can just go running around and then have catchy YouTube videos which says nailed down financial model, something like that. But the idea right now is that it does not really work. If that would have been the case, we will all be billionaires. Why does not really work? The issue is that this is the issue. It's the conditional number is too high. It's 10 to the power 16. What has happened is that these features have actually cancelled each other out in between, and there's no way a human like us can actually understand what's going on right now. We have broken down this simple linear model into such created such complexity out of it that right now it has actually become meaningless. Or in one word, if I had to say, the model has overfitted very poorly. Okay, so that's if you want to really, it's probably like this is how I see most of the academic papers are formed, because there's no money on the line. They do overfitting and then they publish with hypothesis back tracing it out. But that's true certainly, because the amount of literature published does not translate to real life alphas. So there's something missing in over using these ideas. um, okay, so the idea that why this drastic improvement, the idea is overfitting. Uh, and I can make an argument. I've tried to compare it with using simple vector machine or random forest. If you are very versed with scikit-learn packages, you know that there are some machine learning tools which are easy to use, fairly advanced compared to OLS, and then they take care of non-linearity. If you use that, you will find in sample great performance, similar to what I have shown using just the OLS, but out sample their performance is very poor. Uh, so the idea now which we come to is basically the next or the meat of this the talk is that once we have a future feature space, so you can think of it's called a feature space. You had your base features which were sound uh, financial backing to it. Now you create a feature space which has a huge number of interaction factors. They could be 10 cosine of them, interaction of them, division of two factors. So have you ever thought like book to price is actually is a ratio of two factors? EBITDA to, let's say, market cap is a ratio of two factors. So we have been doing feature engineering without even realizing that we have been doing it since the beginning. So, but that's the idea. You can become more imaginative about it, and they might come significant. There could be a financial backing to it also. But don't be like don't shy away saying that our normal OLS model will not be able to handle it. It handles it perfectly. Okay, so now the idea is that, okay, we have these features. They seem to be adding some value. What if I can actually keep these interaction factors, but still not overfit? Can I do that? And I will show a technique which is called lasso, or you can also call it L1 L2 regularization if you are more statistically versed. It's also called shrinkage methods in some sense. The idea is that we have enabled our we have enabled our OLS to penalize factors which actually don't add any additional value. So let's say if adding an interaction factor or any additional factor does not really add a value, we shrink down its coefficient to zero. We say that, okay, its beta is zero now. We don't really care if you add it or not. The model understands it in some sense. So, but you need to provide a penalty parameter. How much penalty you want to apply? So there are different ways to do it. That the simplest way I'm to go show is that in scikit-learn there's a module called lasso cv, and this lasso cv is imported from scikit-learn linear module called lasso cv. You just go there, ask a lasso cv. So cv means cross-validation, lasso is L1 regularization, as I said. And then what it does is that you do your normal OLS fashion modeling in that. Okay, you have imported that. I will go to come to these parts just briefly. But effectively, what you do is that you fit your model passing x and y, and you will get the coefficient that you get for all the factors. They will be of something like most of them would be zero, which sounds strange, but that's true. So let me just show you. Okay, it's going to take some few seconds. But the idea is that when you do a lasso sort of shrinkage method or regression, the model is going to say coefficients of few factors as zero. And now you know that those features you can actually drop from your models. They are not adding any additional value. That's the whole idea of using a lasso. Now there is one caveat to using a lasso is that because it does not throw us any t statistics or p values, it only gives us coefficients in some sense. So because the coefficient of a factor actually is dependent uh, on its scale, how the scale of a factor is. So one has to normalize before choosing that, or no, before actually giving that factor to these lasso functions. So that's why I've actually z-scored them. So z-scoring is effectively a simple way you demean your factor and then divide it by its standard deviation, so that they all have a standard deviation of 1. They all have a same variance. So now all factors are on a same scale. One additional point I would mention is that this is not the most optimum way to do it. There are other ways to do it, so that there is this might create an issue of having a look ahead bias in some ways. But if you are looking at for the first time itself, let's not bother about it. If you have any questions at the end, I can probably point you in direction how to take care of that. But for now, let's say that you z-score your factors, which is effectively you're bringing all the factors on the same scale. You do it same for your y also. Right? Why not do it just for the heck of it? And then just filter out coefficients which have non-zero coefficient. That's the idea. So if I actually do that, the coefficient space I will show you, it will come out to something like that. So 680 nearly factors I had, you can see that nearly almost all of them are zero. It's a great thing. I know that they are not adding any value. Lasso has figured out for me. And the only feature that are adding value are like these, which are hardly, I don't know, 15, 16 features are there. Okay, now what I do, I just go back to my old OLS model, drop every feature that I had, and only just pick the lasso selected features. There are 20 features, by the way. And I just have done again my OLS.fit. And voila, the model that I have got still has a high conditionality number, but okay, let's just for a second say it's still okay. As I said, that in finance it still goes until it's bizarrely out of the proportion. You have kurtosis and skewness in at least of level that I had earlier in previous model. Uh, yeah, this one, although the skewness is little more skewed here, but the improvement that we will see is in the adjusted R square. Although we have dropped the factors, we have only added, if you say, 6 new factors. In our base case, we had 14 factors and adjusted R square of 1.5, 1.6. Now we have about 8%. So just adding 6 new factors, we have improved our model. And any person can say that like that having 20 model is 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 overfitting in some sense, you can say, but then it's grossly is way better than having these 670 features. I think you don't really need to know much statistics to come to a conclusion that. You can actually go and improve this model, but let's not go in that direction right now. But one more other thing I want to just mention is that it might appear that still to some people that okay, this 78% R square is low, but it's not the case. We if a model has a registered R square of 78%, sometimes that feature actually has a great alpha. Although, so I can just mention that new sentiment and then these features which are, let's say, based on uh, alternative data, which is like job postings and the ribbon pack data set. These are like data set which are really expensive and people use it. They also have, they will probably have even smaller R square. And these are the data set you feel that are actually making money these days. So don't expect even them to have an R square of like something like 40 or 50. Just a caveat that one should not get discouraged by looking at lower R square. That's the best we can do. So we will take it. So nothing wrong in that. I just try to plot a scatter plot of predicted using this model.predict. I think we are aware of this function in starts model, and even in OLS, similar way to use the function. Uh, okay, one more thing I would probably point out is that it sometimes look like a noise also. I think I have it later as a comment, but that's the idea that it will look like a noise. Probably the model will get improved if you improve on your frequency. Sorry, if you change around your frequency. Forecasting a 1 day return, let's say if you try to forecast a 5 day return, maybe a week or something like that, maybe a longer term return, it might change the demographic, it might change your R square, it will definitely change your T statistics. That's the mathematical auditory. But the idea is that not to get discouraged in that. I will mention that. So the research paper don't really show these plots, the correlation plots. If you look at the correlation plot, it will all sound gibberish and noise. To actually make a sense of it, you will have to plot a linear fit over it, and then you can make an argument. Yes, the linear fit is some tilted and something like that. So let's not dive into it, but just make a side note that always have a plot, linear plot. At least it's not going the other way around. That's I think that's the base I would say that at least it's not showing a negative correlation. Whatever small correlation it has, but one can make an argument. Okay, there will be a small tinted something line like this, but at least it's not going to negative direction. Just the sanity check. I wanted to always plot a scatter plot, even if it does not really look good. That helps if it's not bad. So yeah, so okay, using this small idea, let's say we have a model now, whatever that model is, we let's not worry about that to improve it further. But let's say we have a model. What this model does is predicts the next day return. That's the base it does. If I actually start to have the trading strategy based on this model, in sample at least, how would I do? So the strategy building part, I've not d- deep dived in it, but just to give a flavor that how I would go about it. What I said that every day I'm going to forecast the return, what I expect today to happen. Let's say before the morning, before the market opens. No, not sorry, the market opens. Let's say today the market is about to get closed, and I've got the close price estimate somehow, uh, like the last 30-minute VWAP or something like that previous minute, and I take a trade on that. If I'm forecasting that my next return is going to be positive, I buy today and then at the end of close today I sell it off. Or if I feel that tomorrow is going to be negative return for tomorrow's, I short sell at the close today and then probably buy it back the next day, end of the day. So that's the base strategy I have like tried to simulate here. What I've done is that so effectively there are two trades: the trade which are shorting and trade that are like being long. That's the whole idea. So the prediction, the dates on my prediction is greater than zero, at least zero. I've called them to be dates which I have to go long. The days where my prediction is effectively less negative, I'm saying that my returns are going to be negative tomorrow. I've just taken them as short dates. And the daily long trade would be my returns, actual returns made on that day by the index, uh, filtered out only for those days. So if you do a lock, you effectively, so this data PRT would be a, it would be a panda series, and with an index of all dates, I'm filtering only on dates where I have a long position. And if it was, if I don't have any position that day, it's just a negative zero return I've made on that day. And then what I've done is that, okay, I think I've little bit screwed here, but okay, let's just roll with it. So what I've done is that I've said that because I'm doing this hypothetical trade every day, I'm not writing a sophisticated strategy. I've just assumed that my cost every day would be something about 5 bips. And I feel that that's in some realistic terms, that's the case because S&P, if you're trading S&P ETF, they are very liquid. They have very low bid-ask spread. So I think 5 to 10 BPS something would at max that would be the cost if you're trading at least decent amount of volume. Um, okay, so yeah, and the short days would be the opposite of it. The days where I have actually uh, predicting that the returns would be negative. -1 is because I've shorted it, and then again, yes, I've taken the same kind of cost of trading strategy. Benchmark is effectively the buying and holding it to for the eternity. That's the idea of using S&P index as it is. There's nothing else, nothing much. It's just the cumulative returns I've taken and benchmark, or I just plotted those strategies here. So this gray is actually the buy and hold. This blue line, sorry, this green line is the long part of my strategy. This red line is the short part of my strategy, and this blue line, which you have effectively, is the strategy which is long plus short. Effectively, short, effectively long minus the short. So that I've already minus there, so just plussing it out. And that's the idea. Like that's very crude way of looking at strategy. And to be very frank, if you're looking for a new factor on alpha to add value, doing this much of analysis would eventually come fruitful. If it shows at least in the theoretical aspect some promising, then you go ahead and do a more sophisticated back test because it takes time, more data. So it's a very crude way of like knowing is it worth even investing my time or not. So at least in sample, if you try to look at it, it looks good, doesn't it? At least to my eyes, in sample, there's always a caveat that this is an in sample performance. But if I had this out sample performance, I would take it any day. It's a smooth line. If you look at this strategy, although like it's difficult to execute as it in the way it is, but even from our like human eye perspective, you can say this blue line is actually much more stable. In a sense, there is less jiggeriness, or you can call it there is less volatility to it. This black line, which is the benchmark, is actually much more volatile. Although it's not fair to compare them both benchmark, but let's roll with it. We are not. We are looking at like bigger picture here. That in that sense, in crux, that's the meat of the presentation. I will just very quickly go through the other things which I wanted to mention is that some ideas if, or some ways how will you go about it. So I will just roll. I will speed up the process of going forward from now on. If you find it's too fast, you can probably like point out. Okay, go over it again. I will do that. So okay, so if I have to think about enhancement from the model point of view, okay, because as I said that this more often is a portfolio construction and optimization process. But if I look at my the first process of able to have a better forecast, and I will have to go about improving my model. One thing I can start with saying that what is lacking in my model itself. So one thing, if you remember, I said it's a high conditionality number. There are few caveats in sense the error statistics are not normally distributed. They are not closer to noise wise. So here I have tried to browse the box plot of my feature itself, the original 14 features I have in the target. So box plot actually gives you what is an outlier or not. There are some outliers, not some, there are huge outliers. So if you're not aware of the box plot, what it does is that these are the lowest and highest quartile, 90 and 10%, something like that. This line is going to be the median value, and these are I think 25th and 75th quartile. I think that's something like that. So if your numbers are actually above and below these top points, these points, it actually shows that those are the outliers, at least in that distribution. So because of these outliers, one can make an argument it's getting difficult for our model to have those non-linear terms added. Even if you increase that scale, there is something is still missing out. So that's why the argument of increasing polynomial features, because if you square a number and then it's far easier to fit the outliers in that way, because a smaller number would get eventually even smaller, and a larger number would get eventually larger. So that I just wanted to show you rationale of why, let's say, I picked a polynomial feature in this case. Other argument would be that one can also look at its feature by z-scoring. So although in time series sessions, in discussion, even Tom pointed out to me that it's not always good to look at time series features in z-scoring fashion. But if they are cross-sectional features, it's really helpful if you try to look at them in z-score. That really comes in handy. So okay, so if I actually z-score these features, okay, this is just the yeah. So z-scoring is effectively, as I pointed earlier, that is uh, you subtract the mean of that feature and then you divide it by standard deviation. So that try to bring all of them in the same way. If you do that, you will notice that it's little better than the first one. Why better? It's because model would eventually have a little better time learning these features. In some sense, you can make an argument that they are like fairly distributed about its mean rather than this one also. It's debatable if you can think in that way, but it doesn't really help. They are still outliers. That's the point I wanted to make. There's another strategy I have come across is that people actually try to time score their features. Sorry, time score in the sense that rather than looking at the whole history of their feature and then z-scoring it, what I'm going to look at a feature. I'm going to look my returns in the last 5 days, and I'm going to z-score based on last previous 5 day or 10 day or 15 day. That's the idea. Effectively, you are going to form a judgment based on a limited window rather than a whole window. So the way to think it that way, try to imagine that way. So if a month has a high volatility, if a week has a high volatility, it's likely that it will the whole week was volatile. So it's easy to compare that week returns relatively to that week returns. It's not fair to say compare that week return to a week which was very low vol or probably was a normal week. There was no news or nothing like that. So in that sense, that's the idea of looking at time z scoring. Uh, and then the period is that okay. So 5 means that actually I'm going to z score it. So okay, so this time z score is a really neat way to do it. So I'm just rolling that period 5 days. I'm taking mean of it. It's a rolling mean, obviously, and so the rolling standard deviation. Okay, you can play around. So if I have it at 5 day, okay, I have to in this code. Let's yeah, you see a very neat plot. Now it looks good. Like if our original features would have something like this, we would our life would have been much more simpler, I would say. But let's say why I have picked out 5. If I picked out 20, it's the same, some sort of same idea. Start doing that. What if let's say I start to pick a rolling day of 250, effectively 1 year with the same idea. So obviously, like the reason I have picked 5, I would be fair, is that because it looks good, at least in the notebook that I have shared, it looks good. But my rationale was that I'm actually comparing the returns made on a given day compared to the return that index made in the last 5 days. It's it's a fairly I would say nice way to start thinking the right direction. It might not lead there. That's the idea, but it's a good way to do that. So let's say if I have z scored times z scored my feature, how does the correlation look like at least in this way? So I've also z scored my feature also and my target also. Mind you, if I actually z score my target, I'm in some sense I'm not forecasting what's my return tomorrow. I'm forecasting its z score. I'm saying relatively whether it's going to be positive, that whether it's going to be more than the return I've made in the last 5 days or less, because it's a z score in some sense. So that's changing what we are forecasting. Okay, so that might become easier for model to do that. So if you actually go in that path of doing it, your strategy would have to get changed, and you have to be mindful of that. So this correlation, if you get, is far better the correlation I have showed you actually last time. There were hardly a factor which has a correlation of 0.8, something like that. You will notice that factors like 4, 5, 6, 7, 8, oh my god, even the volume one has started to show correlations. Mind you that these are not forecasting the next day return itself. Now we are looking at what the relative return would have been made on the sixth day based on the last 5 days. Uh, there's the same idea of doing that. Okay, what if I try to fit the model using the same OLS? I'm going to just go through it. So in this case, the base feature using 14 features, I have an adjusted R square of 13.4 itself. It's a fairly good R square. If I had any model making this R square, I will probably be able to open a fund tomorrow. It's a like $1 billion investment if all my models have such a high R square. It's really difficult to forecast returns. It's one of the most difficult jobs as a quant would have.